Welcome to Modular March. I'm Andy, this is Robbie, and we are The Rollup.
Modular March is an educational experience about all things modular. Enjoy.
The presentation on how to solve rollup fragmentation.
Welcome, Noah.
Thanks for having me on. Super excited to chat about rollup fragmentation today. So kind of a bit of an intro on myself. So I studied computer science at Iowa State University before dropping out after we raised venture capital for NodeKit. My past experience was in building large-scale data analytics pipelines for Big Four accounting firms, as well as building one of the fastest data analytics pipelines for crypto data at Anomalyfi. So at NodeKit, we're building a shared sequencer called Seek. This focuses on providing interoperability between rollups. We're backed by Borderless Capital, Asynchronous CSX, Blizzard Fund, and Polygon Ventures. Our founding team is based out of the American Midwest, but we have additional team members around the globe. So the main problem currently with rollups in general is they provided scalability for blockchains for the Ethereum L1, but in that process, interoperability was completely lost, and we have a really fragmented experience currently. So the current solutions for this are traditional bridges, just like Wormhole, Layer 0, Hyperlane, things like this, proof aggregation, as well as shared sequencing. So a traditional bridge, like something like Wormhole, Layer 0, Hyperlane, any number of these bridges, they work using either lock and mint, burn and mint, or intent-based bridging. So lock and mint means you lock your token on one end, and then you get out essentially a minted version by that bridge on the other end. With burn and mint, you burn the token on that one end and you mint it on the other. And this can be helpful because then you don't have the liquidity locked in one big bridge. So then you don't have the issues around that. And then intent-based bridging requires you to have liquidity on both ends. The reason why we don't see intent-based bridging being a huge thing between rollups right now is all these rollups have their own essentially smaller pile of assets. So intent-based bridging is more capital intensive. You need to have assets on both ends of a rollup. So you need them on the source chain and the destination chain, which with rollups, especially for the smaller modular app chains, that gets really tricky because you need to employ market makers and it gets to be a pretty complicated process. So in addition, none of these options are atomic and they're not synchronous. So they wouldn't really solve the atomic synchronous composability problem, which we've kind of grown to love at NodeKit and try and tackle. So proof aggregation is another great option for rollups to also solve this essentially interoperability problem. So this is an option that is used by different ZK rollups in general. And essentially what you're doing is you're proving two different actions on two different chains. So you're proving a burn of a token on a source chain and a mint of a token on a destination chain. But the main things holding this back are the high cost of ZK proofs, the speed, and also how flexible it is for new VMs. We're seeing a lot of innovations in this space recently with stuff like Hyperbridge for ZK Sync, as well as the AggLayer. But at the same time, we're still not at the synchronous point at this yet. There is exciting developments with these things called ASICs, similar to things we use for Bitcoin mining, specifically designed for ZK proofs. But at this point, it's not synchronous yet. So it doesn't solve the third part of that, which is atomic synchronous and composability.
Yeah. And just real quick on this point, on this slide here, oops, sorry about that. Some of the core issue here with the ZK, because from our understanding, some of the ZK stuff kind of is like this pure end game of interoperability, where you really are you kind of get the best of a lot of the current tech stacks that we have and being able to put them together. But as you're saying, it's still expensive and slow to generate these ZK proofs. So if you want an experience that's like able to actually fulfill like this chain abstraction end game or something, ZK proofs just haven't got there yet in terms of their functionality, but the core underlying principle is there. Is that kind of
exactly
the idea?
Yeah, basically we're still to put it in sports terms, we're kind of in the first quarter. So if there's 4 quarters in the game, we're in the first quarter right now for ZK proof aggregation. So there's still a long way to go, but the fact that we're in the game at all is really exciting stuff. So we definitely think that ZK proof aggregation could be something that does be the end game. At this point, it's kind of hard to determine what the end game would be for crypto rollups in general, because it's pretty wide open space, but it's a very exciting development. So another option to provide atomic synchronous composability is shared sequencing. So essentially, sequencers are operated by different rollups. And essentially, if you share a sequencer among different rollups, you can allow for cross-rollup communication, and you can allow for better interoperability solutions. Current solution for shared sequencing can only guarantee this thing called atomic inclusion. But in the future, people plan on providing atomic execution. And I'll explain that later in the slideshow on kind of what the main differences are between those, because there's a lot of differences, and the end user would be able to use one of those options, but they probably wouldn't use the other. So essentially, a shared sequencer serves to connect all these disjointed rollups, unlocking cross-rollup interoperability. Seamless communication. Essentially, if you can have seamless communication between all these different rollups, you can have a much better UX. Because it doesn't matter if you're on OpStack rollup, a CDK rollup, ZK stack, any number of rollups, you can have seamless communication, making your life as a regular user way easier. And you'll have a better experience. You won't have to bridge between them. It'll just be something that's at the wallet level. Makes your life super easy and makes the regular user be able to use any dApp anywhere, however they want across different rollups. But to understand kind of what shared sequencing is, we kind of got to take a step back and talk about what the heck is a sequencer. Because a sequencer is this thing that essentially all rollups need to have one or more sequencers. And a sequencer is essentially the thing that's ordering their transactions into blocks. So essentially, when you are able to control the ordering of these transactions, you're able to do a lot of really cool stuff for interoperability, which is one of the things that we look into a lot at NodeKit, but a lot of other teams in the space look into it as well. And we think that really sequencing can be this really core unlock. And when you can move to shared sequencing among different rollup stacks, you get super interesting stuff where you can have every single rollup become decentralized, as well as have them share these sequencing powers, which allows you to do a lot of interesting stuff around bridging and oracles and margin and exchanges. And the end game for it's going to be amazing for how you can have synchronous communication across different blockchain networks, essentially, which is amazing to see. And we think it really is a core unlock. So the big benefits of shared sequencers is decentralization, as well as achieving better interoperability. We think these benefits kind of go hand in hand. If you just have the decentralization, it isn't as valuable. But if you just have the interoperability, it's still valuable, but you can't get all the rollups to trust the same sequencer if it's just one person running it. So you kind of need both sides for a shared sequencer to really work. So the reason why we think interoperability really matters and is this big thing for L2s is it allows them to have synchronous composability, better liquidity sharing, and the global state. So imagine if you could write one program and have it be omni-chain by default. You don't have to, this whole writing of cross-chain programs or cross-chain dApps goes away because you don't have to think about it anymore. It's just seamlessly cross-chain from day one by default. So this allows rollups to access every user on every single one of the rollups that is on one shared sequencer seamlessly. Imagine how much bigger your favorite dApp could grow if they could access not only one rollups ecosystem, but 5 or 10 or 50, all on the same shared sequencer. So when the dApp developers get to focus on what matters most, their dApp, not having to source liquidity from all these different spaces. Essentially, it makes their life easier, and it will make rollups be able to have better dApps and better experience long term. So what we really believe the future would be for this space is this addition of what we call an atomic composability layer. With this, you'd be able to do atomic synchronous transaction bundles across all these different rollups, which essentially enables you to have a much better UX overall. We believe for this, it'll most likely be something that will initially be something the users have to create themselves, but over time, there will be front-end interfaces like Intents, like all these different platforms that enable a much easier flow and a much easier experience for the user. So our goal for this, and I believe a lot of the other shared sequencers' goals as well, is for you as a user to not even realize that you're having to migrate or bridge between chains. Just be able to use it seamlessly. So atomic composability is really this defined as the ability to send a transaction that finalizes only if the other transaction in the bundle finalizes. So either both happen or both don't. And currently with shared sequencers, you can only do this thing called atomic inclusion, which doesn't help you nearly as much. So atomic composability, I've heard a lot of people talk about this thing called DeFi being money Legos. That's what atomic composability really enables, is flash loans, yield aggregators, decentralized stables, restaking. All those are really examples of atomic composability. So we think atomic composability is like single-handedly the thing that made Ethereum what it is today. Because if you couldn't interact with other dApps on Ethereum, would things like lending protocols, Uniswap, would any of this have grown nearly as big? In our mind at NodeKit, not really. We think that that's the permissionless nature, this nature of I can build what I want, when I want, how I want, is this thing that's been able to launch massive DeFi protocols and launch this ecosystem as a whole. So we're really excited about how atomic composability can be brought to L2s in general. So the difference between atomic inclusion and atomic execution is atomic inclusion is just, okay, can I include one or more of these transactions in a block? Yes, you can have atomic inclusion, but atomic execution makes sure that they both actually execute. For example, Andy, if you were using like a DeFi application that wanted to use an atomic bundle, if they told you, hey, you can submit these two transactions on two different chains, but they might execute or they might not. I don't know about you, but I probably wouldn't want to make that position if it was like, okay, I'm going to go on two different chains and maybe we'll get there, but maybe we won't. Atomic inclusion can only do that. With atomic execution, you know, you make the trade, it goes on both chains. Both sides of it execute. So if you're doing something like margin or bridging, lending across chains, you get a much better user experience for that. Better guarantees, better interop, more useful for the end user. So the way that we kind of see this getting enhanced is bridges, oracles, and exchanges. This enables all bridges to become single block bridges, all oracles to be able to access global state across rollups, decreasing oracle costs as well as rollup costs, and all exchanges become global by default. So it's a pretty cool change in our opinion, and we think that more and more rollups that interact with these things will grow bigger and bigger instead of getting more divided, because think of it kind of like the first time that banks were able to be interconnected across the country, or the internet coming and being able to connect all these websites together. The websites didn't get smaller because they were interconnected. They got bigger because they were able to get more reach, because chains that would never have previously interacted, their user bases would never have previously interacted at all, now become seamlessly interacting and knowing each other and bridging across and trying new things constantly. So in summary, we think that the usability of blockchains in general can't just be solved by only doing front-end stuff. Front-end needs to change and the back-end needs to change. And the unification of all these disjointed chains is really a big key unlock for user adoption. And we think that overall ecosystems need to be more interconnected. Divided ecosystems aren't going to be the thing that brings us towards this next million or next billion users. We think the more interconnected these ecosystems can be, the better the UX is going to be, the better the UX can be, the more users will end up using it. So yeah, sorry if I went through the slides a bit quick, but yeah, that's everything that we're kind of thinking about and building in general at NodeKit. We think a lot about atomic composability, and I really hope more people dive into it in the future. Bring atomic composability to everybody.
Awesome, man. Appreciate that. Actually gives us more time to kind of dive into a couple different things here. So kind of taking us back here. So let's kind of go over what this looks like now with the current setup of sequencers, and let's kind of dive into some of the changes with this visual. So talk us through what happens when a user on a rollup today submits a transaction, and then talk us through kind of how that looks like in a world where shared sequencing is more adopted.
Yep. So typically the way the user's transaction works with a regular rollup is, so I'd submit it to, let's say I'm working on Optimism. Let's say I'm trying to trade NFTs on Optimism. I know they just rewarded a bunch of their participants. Let's say I'm trading NFTs on Optimism. So I'm trading NFTs on Optimism. I'd connect to an Optimism RPC endpoint. So just a regular Optimism node, just like you would on MetaMask. So I connect to that. That RPC endpoint would forward my transaction to this thing that they call the sequencer. And the sequencer is just one specialty node. So then that sequencer creates a batch. For the Optimism rollups, it's this thing called op node. So essentially that sequencer creates this batch of transaction, which a batch happens every 2 seconds. So imagine you and Robbie and me are all three trading on Optimism. We're all trading a bunch in 2 seconds. All these transactions gets batched up, and then that batch gets submitted via this thing called the Optimism batcher. And that batcher emits it to, in this case, the data availability layer would be the Ethereum L1. So that's how that batch kind of gets submitted in a regular sequencer. So it's all centralized. So if at any point this sequencer node goes down, your experience would get interrupted, and it would be a pretty hard stop of just, oh, the chain is stopped. And that's happened a bunch of times with different chains, not just Optimism, but a whole bunch of different rollups. And that's a real issue, because if you were trading on like the New York Stock Exchange and it just went down out of nowhere, a lot of stuff would fail, because a lot of stuff relies on stuff like that operating during the exact hours that it's supposed to be operating. So we think that for like mass adoption, you can't have things where it's just like, oops, it went down because AWS US East 1 or something like that went down. It's a big UX issue. And then with a shared sequencer, your experience for a regular rollup transaction shouldn't change a ton, which is really the nice thing. That's the goal of all shared sequencers, is for the non-atomic case, so like the non-cross-chain case, everybody's goal right now of shared sequencing is for your user experience to not change, to be able to decentralize without having a worse user experience. That's kind of the big goal around it. So the user experience wouldn't really change. It does require a modification to the rollup source code itself, but the user experience shouldn't really get changed at all. And then for atomic transactions, that does change a little bit, but we think things like intents will really help out with making these cross-chain bundles, because instead of you having to figure out like, how do I make this bundle? And it can be really confusing on how to make bundles and stuff like that. There will be a program that just seamlessly makes it. So instead of you trying to figure it out, you'll be able to go to a website or go on MetaMask and have a MetaMask snap that can do it. So it'll be super easy and just seamless.
Yeah. Now, the follow-up to this that I have, and I think Rob's got something as well, but from what I understand, the pre-confirmations of using a centralized sequencer happen quicker than a shared sequencer, but you still have to get this hard commitment after the pre-confirmation from this data availability layer. And then similarly here in the shared sequencing model, this you've got like these stacks or the shared sequencer provide, there's a difference here in this pre-confirmation and then hard commitment. Could you kind of explain what pre-confirmations and hard commitments even are? And then could we also dive into the differences in the models?
Yeah. So essentially think of the pre-confirmation as it's just kind of the pre-thing that happens before the hard commitment. So essentially it's a faster way of confirming to you that, hey, we've created this block. This is going to be the block for this rollup for this time. And essentially that's giving the user is able to move forward in their design. Like when you submit a transaction on Optimism, you're not waiting for the full 12 seconds of Ethereum's blocks before your transaction goes through. It goes through much quicker. It goes through in 2 seconds. That 2-second block time is by the sequencer itself. So this hard commitment is something the rollup's doing in the background. So the end user, for 99% of the time, the end user really won't be paying attention to the hard commitment unless they're trying to bridge out. So if you, for example, if you made a transaction on Optimism and then you try to bridge a second later, you wouldn't have a hard commitment on it. So if you just got your ETH in the account, you might have to wait a minute or two for that hard commitment, or 21 minutes for Ethereum's finality, depending on the rollup design. They each operate a little bit differently. But in a shared sequencer's design, you would get that pre-confirmation the same, and you'd still be able to receive the hard commitment as well. So essentially, the centralized sequencer will always be faster because you don't have to do this thing called consensus, which is just all these nodes coming to agreement. So when you don't have to do consensus with a centralized sequencer, you can be really quick. But a shared sequencer does have to do consensus, which is basically going around and asking each node, hey, is this the block? Is this the block? Is this the block? And once you get everybody to agree, just like trying to get everybody to agree when you're like ordering dinner, once you get everybody to agree on what you're doing, then you decide, here's the block. Great, now we can move on to the next block. And typically that can happen in 1 second, 1 to 2 seconds, depending on the different consensus models used. Some are faster, some are slower, but yeah. So that's still extremely fast.
Gotcha. So either way, the stacks in the shared model provide the these, you're calling them decentralized pre-confirmations, and then the sequencer in this model or the same stack node provides this pre-confirmation, and that pre-confirmation allows the user to engage with more apps and engage on chain much quicker. But basically what happens is these hard commitments are just in, each action that a user takes on rollups are confirmed quickly, 2 seconds or so with pre-confirmations, and then they are confirmed after about 12 seconds. Kind of like this is part of the blockchain state now, effectively.
Exactly. And different rollups do that confirmation in different steps. For example, optimistic rollups are just posting that data to Ethereum. ZK rollups are doing that confirmation with a ZK proof. So that hard commitment is done in different ways for different rollups. But the nice thing is, for a shared sequencer, we only really have to worry about how the blocks themselves are made. So we worry mostly about essentially how the blocks are ordered, instead of, okay, this rollup does this kind of confirmation, this one does this one. There are some things you have to change with that, but most of the design space is pretty similar across the board, because especially as long as we're talking about EVM rollups, it does get a little more different with different rollups that are on different stacks, but yeah.
Gotcha.
Nice. I've got a couple questions too. I think like one place to start is at the node level. So you mentioned how on the current format of sequencers, these are centralized sequencers, the users submit their transaction directly to the rollup node. So I'm curious, in the shared sequencer model, are users still sending their transactions to only the one rollup node? Or now that these rollups are sharing a common global state, I think is how you put it, can users submit transactions to a node that represents the global state across multiple rollups?
That's one of the really interesting things that we're really excited about, because you technically actually can do that. So there may end up being places, there may being like operators that run stuff where they just basically say, hey, I'm going to run a node for different rollups. And essentially that's how we're thinking about kind of the atomic composability stuff, is the atomic composability layer would be run by kind of these specialized actors that are running nodes for multiple chains. And then it gets really interesting where you could basically be able to run, basically have a user could potentially only have to sign like one or two messages. They would have to sign messages for each of the transactions, but they would only have one endpoint really where they're submitting it to. And then that endpoint kind of dishes it out. Similar intent. So then you're able to do a lot of interesting stuff with that. But yes, in the current design space, you are still submitting to the rollups themselves. And the reason behind that is because the rollups are basically still pulling off their mempool. And if the sequencer has a different view of the rollups mempool than the rollup node, then you can have issues with how the block is being produced. So in the future, we definitely think that there's going to be more experimentation. It's just the space is really new right now. So everybody's kind of still getting their legs underneath them and making sure that everything works correctly. And then we think 2024 is definitely going to be the year where a lot of experimentation happens. A lot of new features come out, intents, cross-chain margin, all these different things. It seems like everything's kind of ripe for the space to explode out, and all these crazy things are now becoming possible all at once, which is really cool.
Yeah. Anyone who supports the efficient market hypothesis should be really excited about this, because it means that prices can arrive at their like efficient market price or fair market price much quicker. Now, like with the unification of all these chains and liquidity. Very cool. All right, I've got another question here, which is on the consensus side of things. So you mentioned that when the transactions are submitted by these rollups into the atomic composability layer, like we see on this diagram here, the nodes in that atomic composability layer are arriving at consensus about what the state is at each of the rollups that are submitting to it. How do they do that? Like, you know, Bitcoin's a proof of work network. They use miners to arrive at consensus. Ethereum like has proof of stake, and each of their validators stake some capital to arrive at consensus. How do NodeKit validators or NodeKit nodes, if you will, how do the nodes in this NodeKit composability layer arrive at consensus?
Yep. So the way that it works is the sequencing layer validators here, they're the ones that arrive at consensus. The composability layer isn't necessarily validators per se. That's more specialized actors. So you'd see that more as like block builders, or you could use people that are doing proofs there. Traditionally, what we've kind of seen is it seems like the rise of composer-builder separation is going to end up happening most likely on the shared sequencer layer. So in this diagram, that's really what we're seeing there. So you really want the atomic composability participants to be really specialized actors, because for reference, some of the stuff could cost a couple $1,000s a year, a couple $1,000s a month to run. So maybe $20,000 a year to run. But when you're doing all these different bridging transactions, there's essentially a market to be made there. So then the rollups are still able to essentially internalize a lot of these interoperability fees. So instead of a rollup having to leak fees to another bridging provider, the rollups can internalize it. So we see this atomic composability layer. This is essentially specialized builders or specialized participants that are running specialized versions of these different rollup stacks. But think of it as these builders take on a little bit of complexity. So then the end user gets a much easier experience, and you still submit to one API. You don't have to worry about, oh, am I going to have to submit to 50 different APIs and get really confusing. A big thing that we kind of think about here is how can I make this as simple as possible? So then when we go to 50, 100, 1,000 rollups, the API stays the exact same. So people can build stuff and not have to worry about like, oh, is this all just going to change? Because the biggest thing for us on why we think Ethereum got so big is the EVM hasn't changed a ton. So people were able to say, okay, that's the standard. I can go build my liveliness on this. I can go put my life savings and say, okay, I'm going to be a dApp developer. People have that flexibility, and until you kind of are able to establish standards on it, people kind of get a little wary on like, can I build on this? Can I not? Because it's pretty risky for new businesses to build on new technology until you've kind of arrived at a standard. So basically the key to atomic composability is standards. So the key to standards is one more standard, but yeah.
Yep.
Nice.
And
nice.
You mentioned proposer builder separation, which my understanding is in the context of validators on arriving at consensus on Ethereum. Now you're mentioning that because NodeKit also arrives at consensus, there's also an element of proposers and builders, and you guys are able to separate those in NodeKit's consensus mechanism.
Yep, we are, and that's one of the main ways that people are thinking about across the space about how atomic composability can be achieved. Everybody kind of has slightly different elements on kind of how they're planning to do it, how other people are doing it. So everybody kind of has different ideas around it. So I don't want to speak for the entire shared sequencing space, but at least at NodeKit, we think the best way of kind of doing interoperability is you need to allow for some specialized actors in the system, because otherwise you'll end up just having everybody try and run it themselves, which, for example, we're using a service today to do streaming. Does any of us know how to code an entire streaming service from scratch? I know I don't. So
neither do I.
We're able to use the tech and it works fine. So you need to allow for specialization. Otherwise it gets really complex. If everybody's got to do everything, nothing would move forward.
Yeah. Yeah, I think that kind of goes a long way with the broader thesis of kind of modularity as a whole. Another kind of important concept that we brought up here is this atomic composability, and I'm particularly curious how shared sequencing stacks up in this kind of competition for roll-up time to finality. I know we touched a little bit on the pre-confirmations and hard commitments and the differences. So I guess let's talk about time to finality using shared sequencing and how atomic composability kind of is part of this or is not. And yeah, perhaps they're two separate things, but I just want to touch on this time to finality, our like kind of conversation that's been happening, because I think that there's a lot of insights about trying to achieve these hard commitments as fast as possible. And then I think that also plays a role in this atomic composability conversation.
Yep, you're exactly right. So with time to finality, it's a humongous factor in this. So different rollups are going to want to be able to do different bridging between them. But at the NodeKit level, for example, our time to finality is sub 1 second. We specifically chose the consensus model. We chose Snowman for its time to finality because having a reorg on a rollup is a much larger issue than having a reorg on like a layer 1, for example. On a layer 1, it's an issue, but it isn't this huge issue. Rollups should only reorg if essentially the L1 underneath reorgs. So that's the only time when you should have a reorg. So essentially, atomic composability needs to be essentially very cognizant of that, very secure. And that's the big reason why a lot of these atomic composability projects are kind of taking a little while to get fleshed out. And that's why we haven't been able to do this these past few years. And they're finally all coming to fruition now, is because we needed the rollup systems to get a little bit more mature in the stack. Because then you're able to build out these systems. You're able to know, okay, here's how this rollup's going to work. Here's how this rollup's going to work. And now that we're starting to see like Arbitrum finalizing some of the stuff in their stack, ZK Sync, Polygon, Optimism, everybody's kind of getting there where they're having these big upgrades, but they're not really having, one of the things we haven't noticed in the past few months is there isn't as many huge changes with them. For example, Optimism has completed Bedrock, Polygon has completed some of their major upgrades. So now that we're kind of reaching finality on the code, you're able to start doing more things with atomic composability, start doing stuff where both transactions succeed or both transactions fail. And you're really able to do more experimental things because we have that core foundation. And that's why we're starting to see the rise of shared sequencers, GA layers, decentralized proving, all these things, because once you have a stable foundation, then you can build the whole house. But until you have that stable foundation, you'd be a fool to try and build out the whole house because it's just going to be constantly changing.
Yeah, let's dive more into this. I think you had another graphic here, or perhaps it was earlier in the slideshow. Maybe not. I mean, this is definitely one where Rob and I were thinking about this idea of hyperstructures where you've got all these interconnected parts. But I guess like let's okay. So in a world where this graphic stands true, and shared sequencing exists, and atomic composability is being reached, like what's next for what comes after that? What's the third and fourth order consequence, whether positive or negative, problems or innovations that kind of come in a world which this diagram exists?
Yeah. So the way that we kind of think about it is think about how you could still use your local bank before probably any of us were around, before banks became like interconnected with all these networks, and before like the internet became interconnected in general, you could still technically use it. And it was usable. And like there was these things called the intranets, which were these smaller internets that were very divided up. But once you were able to interconnect them all, you had a Cambrian explosion. And that's why we had all these websites pop up. We had the .com bubble. We've had the rise of social media, all these things. That's what happens. You're able to do whatever you want, wherever you want, however you want, all these build whatever things, it becomes possible. So anybody could launch a rollup, just like anybody can launch a website. Anybody can do it however they want, and it can be cheap, it can be fast, it can be easy to use. And all these crazy applications, instead of it being, oh, my crazy application is too crazy, I don't want to have to learn all these different things. If you can know how to code, you can make a blockchain application, and you can connect it to all these different things, use it however you want. And we want to make it so blockchain applications are easier to use than regular applications. I want my mom to prefer to use my system than go and use her local bank. Once we've done that, then we'll know that we've actually gotten to the place that we want to be. But we want it to be simpler to use than traditional banking. And that's what we think this provides. So that's why we're so excited about it.
Andy and I are laughing because you used the word Cambrian explosion.
And oh yeah, I know. It's a meme at this point.
I think it rings true. So I'll also add some context around this hyperstructure analogy that Andy and I were talking about last night, which is that if you look at this diagram you have here, all of the 6 L2s in this diagram are connected. And I come from in mathematics, there's a whole class of theories called, and it's involved in set theory. There's one operation in that, which is that, let's say you had all these L2s in, you had a set of L2s, right? In this case, 6, but none of them were interconnected. So you would have no lines, right? You would just have 6 circles within this big set of L2s. Once you connect all of those L2s together, you do what's called a hyper operation. So I don't know if there's
trying to show this one. This is the one.
Yes, exactly. Yeah, exactly. So this would be a traditional set of L2s, right? So once you do this hyper operation, you map from this set to the other set. You map to the power set of L2s. And doing that operation is called a hyper operation. And then there's these algebraic structures that are called hyperstructures. And these hyperstructures are collections of these mappings, basically from a set to its power set. And then you can build these structures on top of one another like money Legos that ultimately create these hyperstructures. And the founder of Zora, one of the popular NFT marketplaces on Optimism, wrote an entire article about these hyperstructures. And I don't know whether he realized that it was a formal mathematical term or not, but he lays out this criteria for building hyperstructures in crypto, which is to be unstoppable, expansive. There's 7 of these criteria. I'll read them out just real quick. Unstoppable, which means that the blockchain is persistent. It runs as long as the underlying blockchain exists. And in theory, this interoperability solution is unstoppable. It could run as long as the underlying L2s exist. He also goes on to say free. There's 0% protocol fee. And in this case, shared sequencing could be made free. Valuable, expansive, permissionless, positive sum, and credibly neutral. And those are the criteria to make up a hyperstructure. So a lot of those are variables that are still up for determination, probably based on what the underlying L2s are looking for out of their shared sequencer. So when it comes to setting a shared sequencer fee, when it comes to the guiding principles that determine this shared sequencer, what is the coordination process for that? Are you guys making these decisions? Is it up to like decentralized governance for like on based on these L2s? Who's making the decisions to, let's take one example for simplicity. Let's say a protocol fee or a shared sequencer fee. Who would be in charge of making the call on whether or not the shared sequencer charges a fee?
Yeah, so it's a great question. And we've actually thought about this a ton, especially in the past couple of months at NodeKit. So we actually have a strategy that's, I'm going to give a little alpha out, but this isn't out there yet, but let's give it some alpha to the roll-up listeners. So the way that we think about it, you need some kind of fee for Sybil resistance. And that's basically you need a fee so nobody can submit 50 million transactions in 2 seconds and then try and crash it. You need a little bit of fee for that. Other than that, and that's similar to how Celestia charges a fee as well, but that fee can be very small. But other than that, for the fees on the L2s themselves, the L2s are still able to keep their own sequencing fees in a system like this because a shared sequencer doesn't necessarily need to be submitting all of the L2s batches to the rollup contract on the L1. So the L2s are still able to keep their sequencing fees. And here, let me pull, here we go, the atomic composability diagram. The way that the fee structures will be set is we believe you should flip it on the head of every single type of fee structure that's in the past. Typically protocols set the fees and like the actor of the protocol set the fees. In rollups, the rollups provide all the order flow. So we think of rollups as kind of similar to how like freight is done, which I know freight isn't the sexiest of things, but if I'm trying to ship a ton of mangoes across the US, that ton of mangoes, the person that's produced a ton of mangoes is going to decide much more about like, okay, who's going to be the one to carry my freight? So if we're saying the rollups are going to be able to set the fees on the composability layer, and the rollups are going to be able to decide. So the rollups are going to be able to incentivize however they want these different actors and say, okay, so you're going to get this percentage of that fee. You're going to get this percentage. And that enables at the rollup level much more control over how this composability is done. So if you want to run essentially like a specialized actor in this that's completely private for your rollup, and you're like, okay, every single transaction that gets submitted to the sequencing layer has to be encrypted using some kind of encryption mechanism before it goes to the sequencing layer. The rollups can do that, and they can determine how the fees are paid out. So the rollups will be able to essentially adjust that, and we believe that that's the best way, because if we just tried to do a broad stroke and say like, okay, all the rollups get 1% of fees on composability transactions, you'd have some rollups that would be thrilled about it, and you'd have some that would be super angry about it. So I think at NodeKit, we think the best way is to allow the rollups flexibility on how they can set those fees, but also provide them kind of templates on that as well, and provide them basically like, okay, here's what the average fee is for all these other rollups. You can set it however you want. If you want to set it at 1%, these composability participants can charge, or you want to charge 1 BIP or 1,000 or 100%, and they take all the fees. You can decide as a rollup how that kind of works, and we think that's kind of the best way to do it. Let the rollups decide it, because their order flow is the valuable part.
Do you think the rollups end up grouping together based on their own biases and prerogatives? Like the rollups that want a protocol fee, they all group together. The rollups that want encrypted transaction pools, they all group together, and then we get these groups of rollups that share sequencers.
Yeah, I think that you could still have the same thing on the same sequencer. So like technically speaking, a shared sequencer could accept a block from any number of builders. So like you could have an encrypted block, or you could have a non-encrypted block. You can even split up the block into multiple pieces. That's one of the things we're working on at NodeKit, is kind of a chunk-based approach. So our blocks are not one piece. So that's how we're able to support different DA layers, is our blocks are made up of mini blocks. So then you're able to, so for example, you could have something like a fully encrypted rollup that has one chunk, and then you could have a rollup that does like first come, first serve. You could have a rollup that does traditional block building. They can kind of change it up however they want, which makes it really flexible for the rollups. And a big focus for us is around rollup revenue redistribution. The biggest questions rollups ask us are about, how is this going to affect my rollups revenue, and how can we actually achieve interoperability? And those are always top of mind in any of these decisions we make. It's always surrounding that, because we want rollups to have a better experience using a shared sequencer, not a worse one. And we think we have a big opportunity to impact this industry in a hopefully a great way. So we think hard about that, and really want rollups to succeed.
Yeah, sorry. I thought
All good.
that was the last part. So you can bring a rollup with like one rollup using Celestia's DA, one rollup using Eigen DA, one rollup using Ethereum in the post EIP 4844 world, and you can sequence all of them in the same block in NodeKit using like this chunk form. So any EVM rollup, basically, whatever parameters, if they have, like, so do they have to be separated? Like, is it something that the rollups prefer? Like, if one wants to have privacy embedded and one doesn't, obviously there's like a separation there. But if I'm using Celestia and I'm using Eigen and I'm using Avail, those need to be separated because they are they're being pointed to different contracts. So that's kind of why they need to be separated. How does that work?
Yep. So think of a chunk as a block. So a chunk is just a block for a specific DA layer. So you could have multiple rollups all inside one chunk.
Okay.
But a chunk's DA specific. So that's how we're able to support different DA layers, is you're able to be able to prove, okay, is this everything that we meant to send to this DA layer? And just like with a rollup being able to essentially on Celestia call a function, be able to say, did you withhold any data? We're able to do a similar thing because we make it for each chunk. So that's how that would work.
Yeah.
Hope that answered your question there.
So each chunk is like, it's set for a specific data availability layer. So NodeKit is agnostic, can be in the future when there's more data availability layers, you can add them in to your code in some capacity. And you can then, so in the future, the NodeKit blocks could theoretically be split into a lot of chunks if there's a ton of different DA solutions out there.
Yeah. Basically, we can split it up pretty heavily on that, as well as we basically run into the issues of networking at a certain point, which any computer science person would tell you. If you're running into networking as your main bottleneck, you're happy of how you're doing. So, yeah.
Oh my goodness, I'm so.
That's how we're thinking about it.
Well, no, I think that this has been fantastic. I really appreciate you opening up the floodgates for shared sequencing and spending some time with us today.
Thanks for having me on. It was great to chat about everything from composability to DA layers and all bit in between. Thanks, guys.